To electric motors. Electric motors are very versatile. You'll see almost some electric motor everywhere. We'll cover two types of electric motors, brushed DC motors and brushless DC motors. The motor which you used in your lab are brushed DC motors, as it will become clear. A brushless motor has some advantages, but we've not really, and they're a little bit more complicated to operate. We'll see them too. So the basic principles of brushless DC motors, brushed DC motors is through the electromagnetic principle. What is happening here is there's a coil. Okay, and this is connected to your voltage source. And then there are permanent magnets. These are permanent magnets. There's a north and south. Now, what happens here is that these magnets produce a magnetic field, which is shown here as B, right? And the magnetic field is always from north to south. Because you're passing a current through the wire, this current I. And now because there's a current and the current carrying conductor is subjected to a magnetic field, it'll experience a force. You can find that force using Lorentz law. So you pretty much have to do I cross B. So if you do I cross B, let's do that here. I is this way. B is to the right. And so if you do B, this is better. Okay, so I cross B, my thumb points downward, that's why the force is downwards. And similarly, you do it to the left half, and you'll see that the force is upwards. So you see that there's a force acting downwards on the right side, a force acting upwards on the left side. And by that, because it's a force acting same magnitude, but acting in the opposite direction, it's going to induce a couple of torque, which will rotate the wire. Now you see that this funny connection, it's not just a wire, but it's connected through this black sort of half ring. It's called a commutator. And then these things are brushes. So the reason why you want to have a commutator is because once this wire turns 180 degrees, if you don't have commutation, then the current will flow in exactly the opposite direction, which means now the force, which was this way, will become that way. So it will keep oscillating back and forth, and you don't want that to happen. And so the split ring actually ensures that the current always flows in the direction shown, and that way the forces are maintained, which means that it spins in the same counterclockwise or clockwise direction. Okay, so some terminology here. In a motor, the part which moves is called a rotor, and the part which is stationary is called a stator. So you'll notice here the stator is the permanent magnets, and the rotor is the middle part, is in the middle. It's composed of the wires. Okay, and the explanation which I gave is right here, so you don't have to remember what I said. Now we can do some calculations to figure out what exactly is the torque coming from a single wire. So here is that same setup. Now I've put some dimensions, W for the width. That's the only thing I need, width, I, F, and B. So here, this is the front view. We have the force, which is a couple now. That force, if you resolve the force and you take the cross product, right? The torque is the moment arm cross F, then you get torque equals B times I 0.5 W sine theta. But the key thing here is that if I, B, the current magnetic field, and W is constant, so the torque is going to be proportional to sine of theta. What's theta? Theta is the angle made by the normal with the magnetic field. So what you'll notice is that if you draw the torque as a function of theta, it'll actually be sinusoidal, right? The reason why it's not it is not negative is because the current direction is going to be the same. It's when it says sine, it's really the magnitude of the sine. So you see that there's a hump. It goes to 0 when sine goes to 0. Now, when you use these motors, you'll see that the torque doesn't go to 0. It remains more or less flat. The reason why it's flat is because you don't have one coil, but you have n coils. Okay? And so the current you see is basically the average over the n coils. So when you have, for example, 6 coils, you'll see something like this. This is called, by the way, this is called torque ripple. It's a phenomenon which you really don't want to have in your motors. Doesn't really help you to control anything if you have torque ripple. So this is with 6, but if you have like 10 or 15, you'll see that it becomes more or less flat, and that's what you want. So really, it's not one wire, but n wires. Now, when you download the spec sheet of motors, you'll see there are two important specs. One is the stall torque, and the other is the no load speed. The stall torque is the torque when the speed is 0. So power the motor, put a voltage through it, and hold the shaft. That torque which you need to hold the shaft is the stall torque. The other one is the no load speed. So just connect the motor to a voltage and let it spin freely. When the torque, the external torque is 0, the speed which it spins is called the no load speed. Okay, and so we'll come back to these specs a little bit later. I'm going to talk a little bit about the few kinds of motors we have. This is the motor which you probably use in the labs. It's a DC permanent magnet motor. Essentially the same figure I drew earlier. There's a stator, which is a magnet. There's a rotor, which is the wires. And if you look at the torque speed curve, it looks something like this. And then if you look at the torque current curve, it's more or less linear. Okay. Torque is proportional current. Now, this is kind of complicated and also very interesting. What you notice here is that there are two regions. Here you have region 1, which I wrote down. You have the speed is maximum, but the torque is close to 0, right? And here we have the speed is 0, but the torque is maximum. Okay, this is, by the way, the stall torque, because the torque at when the speed is 0. And this is the no load speed, which is the speed corresponding to no loads. So this is at a fixed voltage. Fixed voltage. So one of the biggest limitations of motors is that you either can get high torques at low speeds, or you can get high speeds at low torques. So high torques at low speeds is this, or high speeds at low torques is this region. So those regions are far apart. Many times, if you have applications which require high response, high torques at high speeds, like a video I'm going to show you, then this particular curve doesn't really help you because you don't really get maximum torque at maximum speed. The only way you can escape this is to actually power this motor so that you the torque, you go at a high voltage, then you'll see that as voltage increases, these lines become parallel, and then at high voltage you can get torque, but you still have this problem that you always will get high torques at low speeds and low torques at high speeds. Okay, so these motors, which have a permanent magnet, typically have low horsepower. Horsepower is the power provided by the motors. HP is a unit for powers, as it's basically called horsepower because it was in olden times, people measured power by the amount of power generated by horses. And so this is like amount of power it would generate would be approximately that of 5 horses. It's 746 watts is 1 horsepower. So it's 5 times that. Okay, and I've listed a few applications of brushless DC motor. One thing which might be familiar is you probably use a servo motor in your lab. The servo motor is nothing but a DC motor fitted with a encoder or a position control sensor. So once you have position control, you can make it go to a precise angle. Okay, and we'll also talk about stepper motors just a bit, maybe next class. So that's the permanent motor. There are a few other motors. There's DC shunt motor. Here, essentially, instead of the permanent magnet, you have windings. You have the windings in the stator, you have windings in the rotor. So here the windings are in parallel, as you can see. The result of this setup is that you get more or less constant speed for a varying load. So no matter what your load is, the speed is constant. Something like this is useful if you want to have ceiling fans, you want to power them. You want to probably have constant speed at different loads. And so you'd use these in fans, blowers. A simple change in the setup, connect the windings in series with the rotor. I made a mistake here. This is series. Then you have what is the DC series motor. What happens with this is that you get a very high torque at low speeds. So you remember that DC motors have approximately a curve which looks like this. So the torque is sort of capped, but here you can go a little bit higher. And that's good because now you can use this to power things which require a high initial torque. Okay. One of the biggest problem is that if you don't have any loads on them, then they actually start spinning so fast that they can damage themselves. You can see that this goes to infinity. So you don't want to operate them with under no load conditions. Now the last one is to combine both. So you have part of the windings in series, part of the windings in parallel. And what that does, it basically combines the advantages of shunt and series motor. So the torque curve looks like this. You can see there's a high torque, high starting torque, but you also have some constant speed. So it sort of combines the advantages of both. The problem with the last three I talked about, not the permanent magnet, is that they do not reverse their motion. When the polarity is flipped, they only operate in one direction. So that's one of the problems. You might have to change the circuitry in order to do that.